So this is still module 4, I'm calling it, but we did module 4 and then we did module 4B, and then we're doing module 4C now, continuing on that same theme. And we're going to talk mostly about multi-threading, and again, trying to tie it back to the project for the class 2 to help you guys get going on that. So, list of stuff. So we're basically talking about, you'll see the term reentrancy, reentrant code. It just basically means that your code should be written assuming that you're going to have more than one threads going through the same block of code at a time. And so you can't write your code such that you think you've got exclusive access to any of these resources, because from one instruction to the next, you may get interrupted and another thread may come in and execute the same lines of code. And you need to make sure that the two of them are pointing to different context, or that you're locking your resources somehow, that one person is able to access it and the other person waits in line until they're done with it and gives it back, and then they can access it. So that's what we're talking about. And there's a number of different convenient ways to do multi-threading, and we also kind of lump event handling in this too. So we'll talk about all that kind of stuff. And if you're going to do any kind of Windows Forms application at all, knowing how to do all this stuff, it brings up the whole, you have to do all the work from the UI thread. Okay, well, how do I get around that restriction kind of thing when I need to do what I need to do in the UI? So we'll talk about some of those patterns and gotchas also. And just along the way, just kind of absorb the terminology and how I'm expressing and describing this stuff. Yeah, and then all pursuant to, hopefully at some point, knowing how to create a game loop in our Windows Forms application. And if I have time at the end, I'd love to show you where I'm at in creating my version of it too. Okay, so a long time ago in a galaxy far away, we had these CPUs, and you know, it's kind of interesting. You turn on your computer and it would sit there at this little prompt blinking at you, and it might say, enter today's date. It's like, really? You don't remember? I just turned you off and back on, and you don't remember what the date was? No, it doesn't keep any of that. It would throw that away. You'd have to enter the date. You'd have to enter the time. And then once you were in there at that blinking prompt, you could issue commands, but it was only you doing it, and no other threads, nothing reentrant, nothing. No parallelism at all. So then that's our starting point. Then all of these other frameworks and abilities have been added after that. And as they've been added, the patterns have evolved. And so I really only point that out to say the reason why things are the way they are, it's because of something. If you kind of understand where we came from, that it probably informs how things got to be the way they are. And, you know, I've been guilty of this too. I learned some really cool, elegant way of doing something, and I think, well, why isn't all the code that I'm seeing that everybody else wrote doing it that way if it's so cool? Well, it's because it was written when that wasn't available, obviously. So the other, you know, other than just being able to do things in parallel in our algorithms, one of the big drivers for parallelism was at the hardware level. You know, the CPU became blindingly fast really quickly and evolved very quickly. Memory evolved behind it, but memory isn't as fast as your CPU silicon is, and so you have to have buffers where the CPU says, hey, you circuitry over there, could you go get this chunk of memory from that chip over there? And it like, in CPU terms, it's like having a trail of camels going across the desert, getting the data, trekking back through the mountain pass and dropping it at your feet. And then the CPU says, oh, you again? And uses the data. And then when we include disk drives, where you actually have a little spinning disk there and a magnetic head reading the thing, that is like eons away. You know, it's like sending off a request for data from the hard drive, and the CPU's grandchildren are there when the data comes back from the hard drive. And so the CPU has to basically just go into a wait state and it just sleeps. It says, well, I don't have anything to do until I get my data. So it just kind of pauses and waits, and it checks periodically. And that checking periodically wasn't as efficient as just saying, look, I'm just going to go to sleep, hit this button to wake me up, like the doorman at the hotel. You know, they're basically sleeping under the counter until they hear the bell go off. That's the equivalent of interrupts. So when the camel train gets back across the desert and they drop the data in the box, they hit the bell and the CPU wakes up again and says, oh, okay, I'm ready to go, and processes it. So I know I'm abusing the analogy, but it really is kind of like that, all this parallelism between devices that operate at different speeds from one another. They go into these wait states and then use interrupts to get informed that they're ready to go continue that work that they were working on. So we also have, you know, when we talk about our algorithms, as you know, computers were really expensive and they filled an entire room. So maybe a university had one room that was made up of their computer, and then some other room they had a whole bunch of desks like this with dumb terminals where the students would communicate and send their programs to the mainframe to have them executed. Well, if you have a whole bunch of students sending their program over there to be executed, the computer is constantly working as fast as it can, but we implemented algorithms called time sharing, where it would say, okay, I'm going to give 1 second to your program, then an interrupt is going to fire after that 1 second, and I'm going to yank control back from you, and I'm going to give it to the next student's program for a second. An interrupt would fire, I'd yank control back, and I give it to the next one, and they share the CPU time across all the other student programs that are in the queue. And when you expand that to the business world, they would say, we're also going to do a little bit of accounting to say we gave you 1 second of time, another second of time, another second of time, and at the end of the month we'll send you a bill for all those seconds of time that you used during the month. So it became really important to make sure you debugged your code on a piece of paper first, and you knew as best as you could that it was correct before you even submitted it, because you were going to incur more costs. You know, and at 2 a.m. in the computer lab at a university is not where you want to be hitting the retry button too many times. Now we live in a beautiful time, right, where you can hit the submit button on these mind tap exercises as many times as you want to, and it's free and pretty darn quick.
Yeah.
So, but that's time sharing. So that's another way that we use parallelism and interrupts. So then along came Windows in the 90s, and Windows, is, as we've talked about before, is based on this event system where we fire events and handle events, and all of your Windows controls, your buttons, your text boxes, your list boxes, everything is based on events. And you know, you click on a button, an event gets sent to your code. Your code has a loop somewhere down in the bowels of Windows that's sitting there saying, do I have any events for this window? Nope, go to sleep. Do I have any events for this window? Nope, go to sleep. And then finally it says, do I have any events for this window? Yes. Okay, well, look up and see who the event handler is for this event and call that function. Okay, good. And then it goes back to sleep again, waiting for the next message. And so it's the same thing. It's just a game loop in an event-based system that is doing time sharing among processes using interrupts. But it utilizes all that stuff to do cool things like presenting a nice, pretty graphical user interface. So we like it. Yeah, and so all that to say, just assume when you write a function, you know, a method in one of your programs, it might not run continuously. Some interrupt may come in from the side, yank control away and go do something else, and then come back and give you control back. And all that stuff that happens in between there, what we would say in the cybersecurity area is that presents a number of attack vectors that can be exploited if we don't follow good established patterns and that kind of prevent those, shut those doors in the face of the people that would want to exploit them. Okay, so that's the context here. So reentrant code would be code that expects there to be multiple threads and they're sharing the same data or access to the same device. So imagine that you've got two windows sitting there and they're both reading a file from the disk. Well, there's just one disk and there's just one read head. And so we're going to have to use these techniques to say, no, it's my turn to use the disk. I'm going to read my stuff. And then when I'm done, I will fire the interrupt that lets you know that it's your turn, and you grab your turn and do your thing. So if you just kind of think of it conceptually as I need to lock the resource that I'm using and make it exclusively accessible by me while I'm using it, that's generally the theme of what we're going to. And then it just kind of gets fancier, and we'll go through some of those different combinations that have evolved since the simple ones. So a couple of examples that are, these two are among two of the ways that you can think of trying to harden your code. But let's say, so within Windows, there's a whole bunch of, we call it user mode up at the top where all your applications play and they talk to each other and do what they need to do with user interface manipulation and all that. And then there's kernel mode down at the bottom. And all of the protected access happens and the refereeing goes on at kernel mode. So there's obviously things that you can do in kernel mode that you can't do in user mode. Trying to think of an example of one of those, but I mean the file access, right? Mm-hmm. The kernel code would make sure that you don't enable write access to a file for which you only are supposed to have read-only access. Well, if we have these little buttons in Word now and Excel where you open a spreadsheet or you open a Word document and it says, do you want to enable editing? Yeah. Well, if you don't have permission, you might click that thing all day long and it says, no, you can't have it. But what if you were able to say, well, I have permission, so I'm going to enable editing, and then some other window running on your computer, some virus or something in the system bar says, oh, that's cool. He just clicked enable editing on this file, so I'm going to take control of it and I'm going to do a bunch of editing, right? They're exploiting your permission to elevate your access to do something that you're allowed to do, but they aren't. So my analogy there is you opened the gate and other people found a way to get through while access was elevated, and then maybe you don't even know it, you're not aware of it, so you're finished doing what you needed to do, you unelevate, you go back to read-only mode, but the damage has been done. So that's one way of thinking about the attack vectors and how you can harden your code. Another way is kind of the inverse of that, where you have permission to unlock the resource, so you do so, and then they say, well, I can't figure out how to get through the gate myself, so I'm just going to break your leg. I'm going to cause your program to crash, or I'm going to starve your program of resources in some way to make it where you can never complete your task. And now, even though I wasn't able to get access to it, I've denied everybody else the ability to get access to it too. So it's a denial of service attack. So even when you think, well, I'm not allowing a bad guy to get in there and access the data, if you allow the bad guy to prevent anyone from getting access to the data, it's just another form of attack, another form of attack vector. So you got to worry about all this stuff with trying to make your code reentrant.
Yeah, I actually didn't even think about that type of stuff. Yeah, I don't think about the security aspect of it all.
Yeah, and that's just two. right? You know, that was one of the interesting things about working in Windows
Yeah.
is every month we would have a pile of these security bugs to go through, and we'd sit there and ask, well, how in the heck did they get access to this? I'll give you an example. In the old days, scheduled task manager, it was it was really cool. At the time, everybody thought this was awesome. This was very robust. That there was a file, like an XML file, that defined all your tasks. And if you went through the user interface and you set up, okay, I want this program to run every Monday morning at 10 o'clock. And I want this program to run on the last day of the month to do all of our reporting for taxes or whatever your tasks are. You've set that up in Windows in the Scheduled Task Manager UI. Well, you can export those tasks in an XML file, and you can copy them to another machine where you also want them to run. And what you do is you go under the C:\Windows tasks folder, and you copy that and paste that file into that folder, and Windows is watching that folder, and it says, oh, look at that, a new file just appeared in this folder. I'm going to go read it and create all those tasks for you automatically. That's a very cool feature. Well, later they decided, yeah, we don't really want it to work that way anymore. It's not how we do things in Windows.
Yeah.
But for backwards compatibility, they had to continue to support it. So a decade goes by. The operating system, the security model, the threat vectors, the file access, all of these things, new device drivers, new kinds of devices, USB drives, all of these things evolve since that feature had worked that way and now is still being supported backwards compatible. Well, what somebody realized is these two kind of examples, they could get access to the folder and write to it to change the definition of the tasks. Or they could delete the folder and cause the tasks to go away with a denial of service attack. I'm not giving the exact details of the bugs, but they found out that they could do that. And it was related to other file system access stuff where the person wasn't technically supposed to have access to write to that folder, but through some other vector, they got access to it, and having access, they thought, oh, well, if I've got access, what can I do with it? And scheduled tasks, that was one of the things that they could do with it. Well, then you realize, well, the scheduled task manager is not just for, hey, run this program at 10 o'clock every Monday. It's also used very heavily by the Windows Update process. When Windows Update says, hey, guess what? It's Tuesday, Patch Tuesday. It's time for you to do your update. It's a scheduled task that runs to go out to the internet and check to see if there's any updates to do. Also, when there's a lot of these things like system files, system processes, configurations that can't be updated while you're running Windows, they have to be done at restart. So what do? They create a scheduled task to run on startup. So a lot of that stuff with the ins and outs of Windows Update have to do with scheduled tasks and the infrastructure underneath it. So if you can exploit scheduled task manager, there's a lot of damage that you can do, a lot of pilfering that can go on. So anyway, yeah, it's important. So that was some of the stuff that I got to mess with, security related, with reentrancy. So I'll go through a few of these. Now these are just, think of this more as conceptual. You know, if we were doing an algorithms class or a security class, maybe a networking class, we'd probably focus a lot of the semester on doing examples where you have problems proposed to you that you have to use these synchronization objects to solve the problem. But for the scope of this class, all I'm doing is trying to just introduce you guys to the concept so that next time you see it, you'll think, oh, yeah, Dr. Snyder told me about that thing. Okay. So you guys, I'm sure, have heard of the game or seen a movie where they had this game where they have the little stuffed rabbit or something, and you know, if you throw the stuffed rabbit to somebody, it's their turn to speak. You know, in the sharing ring, you know, whoever has the
Oh, yeah, yeah, yeah.
whoever has the stuffed rabbit is allowed to speak, and nobody's supposed to interrupt them until you raise your hand and the person throws you the stuffed little rabbit, and now it's your turn to speak. You know. Well, that's an example of a mutex. Mutex for mutually exclusive. You know, only one person is able to speak at a time, and the resource is the little bunny or the ball, and that's the object being used to synchronize access to being able to speak. So, mutex ensures only one thread can access that shared resource, the ability to speak in this case, at a time. All the other threads, everybody else in the circle has to wait until it's their turn, which is denoted by them having the object. So think of that as a variable that holds an instance of some object. Maybe it's a string, maybe it's a custom object that you created a class for, right? But you have some instance of this object, and if you have the object, then it's your turn to process or get access to the disk or write to the file or talk across the network or whatever. Then you put the object back and somebody else gets a turn. So that's a mutex. Next one is called a semaphore. And the classic example of this is, like it says, so we've expanded it basically. It's the same idea. We're controlling shared access to a resource, but now we've got multiple bunnies, multiple stuffed rabbits that can be passed around. And the example breaks down because, well, it doesn't make sense to have 3 bunnies and have 3 people talking at the same time, right? So we change it to, let's say it's chairs at a lunch table, but only, let's say 3 people can eat at one time. Everybody else is standing there holding their tray. So it's your typical Chick-fil-A, you know. Yeah, so it's the same concept. It's just that we have multiple opportunities for the people waiting for the resources to have the resource at one time. And, you know, you can obviously expand or shrink the number of those lock points, if you will, with this. So in essence, it's a similar kind of object, but instead of being a string or something else, it's some kind of an object with an integer counter on it, and the integer would indicate how many are available. And as somebody says, hey, I need the bunny, it would go from 3 down to 2. Now I have 2 bunnies that are available. The next person would request it. Now it goes down to 1 bunny available. The third person gets their bunny, and now we've got 0 bunnies available. So the fourth person that asks for the bunny, they say, oh, sorry, you're going to have to wait. I don't have any more bunnies until somebody gives their bunny back. So pretty obvious. And that's called a semaphore. So mutex is 1, mutual access, mutually exclusive. Semaphore is multiple of them that are mutually exclusive. Next one is a monitor, and think of this as a, you know, another example. You got a study group and you've got one notebook, and when somebody wants to write, they ask for the notebook, and essentially you might think, well, what's the difference between this and the ball? Well, the monitor is, it's like the resource you're protecting is the ball, is the difference here. So you're wrapping the monitor around the object that's shared in this case. Yeah. And the cool thing about this one is it's built into C#, and so some of these, they don't have a huge differentiation between the others, except that it's really convenient to use them, like the lock. So in C#, I think that's wrong. I think that comment is wrong. I have it backwards. I put it on this one, and this slide is correct. In C# we have a lock. If you jump down to the example, I can say lock whatever the resource is, and inside the curly braces, whatever code that I put in there, I have exclusive access to that object while the code inside the curly braces is executing. Any other thread that comes down and is executing the same lines of code, when they get to the lock, they realize that that object isn't available and they wait. So, and this is a easily approachable example. You know, you go to the gas station and ask for the bathroom key, and they have one, and they give you that bathroom key. So, pretty easy. So, summary, we start with the ball passing game for who gets to speak. That's a mutex. If we expand it and include multiple speakers, that's a semaphore. If we add a policy for who gets to go next, that's the monitor. And I don't think I made that clear when I was describing it. So a monitor, you can define rules. Let's say it's the bathroom key at the gas station, but anytime a female comes to the gas station attendant and wants the key, they always get the key first before any of the guys that are standing in line. If we had a policy like that, you know, maybe a better example would be like the classic nightclub example where you got the wall with all the guys lined up on the wall waiting for an opportunity to get in, and some girl walks up to the front of the line and they just let them in immediately. That would be more kind of a policy that would go along with using a monitor for who gets to go next. You might see this also in like priority queues where you have a file maintenance process that whenever it's time for that to run, all of the people that are doing transactions have to wait for that file maintenance task. It gets to go to the front of the line and gets to do its thing. And then, so all of the processes waiting to do transactions in that line are able to use it if it's available, and there isn't a file maintenance process also waiting. That would be another example of a policy. So, yeah, so just ponder the applications for this, the different combinations you might be able to imagine, try to imagine some of them and how you might use that different kind of a monitor. I encourage you to Google these, you know, look up the classic examples of these and become more familiar. You know, spending time reading one web page about each one of them would probably give you a much better, deeper inspection of them than I can do justice to here in a few minutes in class, because we've got to get on to other stuff. So back to the Windows reentrancy stuff. So we got these Windows controls. And the big point to make here is Windows was written in C, and then some parts began to be in C++. I always kind of made fun of most of the developers that I knew at Microsoft because when the Microsoft compiler started supporting C++, it was, you know, they were proud of the fact that, oh yeah, Windows is written in C++. Well, it was written using a C++ compiler by hundreds of developers that wrote C programs. They were just using a C++ compiler to compile their C programs. It didn't change that quickly. It didn't evolve very fast. So when all of that code was written, it was back in the days when we didn't have multi-threaded, you know, hyper parallel personal computers, so they didn't need a reentry. So none of their patterns, none of the patterns required to support multi-threading were a priority back then. So while there may be portions and even much of the code that's underlying Windows that you'll be okay using in a reentrant fashion, it's important to remember that Windows code out of the box is not guaranteed to be reentrant. So any Windows programs that you build yourself, you need to take care of to make your code on top of Windows reentrant, not assuming that so for example, a classic example is you're supposed to single click to activate buttons in Windows, right? How many of you have a grandma that double clicks on every button? Click, 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 click on all the buttons. And so 2 button click events would get sent to your Windows program. So now you've got 2 threads going through, or 2 events queued up in the Windows message queue that are both a click event on the same thing. If one of them starts executing and gets interrupted and pauses, like let's say waiting for disk I/O to finish, then the other one starts running, and it could mess up the data that you're expecting to be the same when you get back. And so that's, exactly the kind of stuff we were talking about with problems with reentrancy, and you just need to assume that it's not safe. But the way that manifests itself for us is when we're writing our Windows Forms applications in C#, we want to make sure that our UI controls are only getting updated from the main thread. Now, if you're not doing any multi-threaded programming or parallel stuff or background threads or worker threads, any of that kind of stuff, this is not really an issue. So last semester, when you're writing a program that just has a bunch of buttons on it, and when you click the button, it runs some code. When it's finished, you click another button. You don't have to worry so much about this whole modifying things from non-main UI threads. But in the kind of stuff that we want to do now, you are going to have to worry about that. So we have this thing called invoke, which is just a little C#.NET trick that says, go check and see if the current thread is the main UI thread, and if it's not, send an event the long way around the barn back into the message queue and package up all the stuff I was supposed to do here, so that when that event gets picked up, it does it from the UI thread and restores what work you were supposed to do. So there's overhead to it, there's a potential delay, it slows things down, it uses a little bit more memory, more handles, all that kind of stuff. So it's not the kind of stuff that you want to do if you don't need to. But when you need to, when you're operating from the background thread, you have to do it, because if you try to set the text of a button or add text to a list box or anything like that from a non-UI thread, your program's going to crash. It doesn't have access to the memory required to update those controls. I don't like, so let's say you've got your main Windows Form class here, and you create this other class that's doing your background work. Well, you could pass it the reference to your Windows Form or the control that code needs to have access to, and you could write all the UI code over here in the other class, the other functions, right? But like we talked about in a couple of classes ago, that directly couples those 2 classes together. And let's say you rename the button over here. The code over here in this class is going to break. We don't want to tightly couple the code together. So the way I like to define my code in these cases from the get-go, and it's a pain in the butt if you don't do it self-discipline like that to start with, to go back later and say, okay, I want to decouple and pull these things apart. I don't want this code over here to be dependent on what I named my controls. Here's another big driver for that. When we want to get into writing mobile and web applications. So one of the coolest things that I did when I was living in Seattle outside of work was I wrote this application to let umpires evaluate one another after they worked a baseball game. They could just say, hey, you could be a little quicker getting to first base, or you need to be in this position in that situation, all of that kind of stuff. But the cool thing about it was there was a Windows program, a web page, an Apple program for an Apple device, and an Android app. So I supported all 4 of those platforms with the same code. Well, then if you're doing it that way, you want only the UI code in each of those 4 applications. And all the other code that isn't specifically dealing directly with the UI, you want to push off in these other classes. You want to decouple any of your business logic from what you're doing in the UI code. Because any code that you put in there, you're going to have to copy and paste that and get it to work in all 4 of them. So any code that you put down in the in the base code, in the common code, is shared across all four of them. You only have to do it in one place. So that's another big driver for decoupling, because it allows you to support any old platform that comes along later that you want to with minimal work. I mean, obviously you had to do the UI code, but all your business logic is somewhere else. So anyway, so the way you do that, circling back to this, is when you define an event where you're going to communicate between the background process and the UI process, is you make it abstract. You don't say, set the text of that button to click me. You say, it's time to change what I tell the user, you know, the state of the application is now I'm able to be activated. And when you send that event, the Windows application says, okay, fine, set the button text to this. The web application says, write some HTML that does this. The Android application says, you know, whatever. But let them deal with how you implement that and be abstract with the nature of the event that you define. And sometimes you have to be kind of clever with it and it gets hard, but the concept is there. Yeah. Okay, so a quick example. I've got a few different things that I want to show you how to do. First one, we're just going to create some long-running process. I'm just going to write a program that counts to 10,000, okay? The first way we're going to do that is we're just going to click on the button. We're going to change the cursor to an hourglass and let it sit there and spin while we're working. The UI is completely unusable. It's locked while it's busy running the code, and the user has to wait, and when it's done counting to 10,000, then we're done. We can use the application again. So let me show what that looks like. Let's look at the code real quick. You guys see that? Okay, so we're going to, this is how you change the cursor. I don't know if you guys did that last semester or not, but you know, cursor.current is when your mouse is over that window, use this cursor. So, you know, where is it? You know how you can, okay, the cursor changed to a right-facing arrow and then changed to a left-facing arrow. That's because it happens to be over that particular Windows control. And so each Windows control can tell you what cursor to use. And Windows keeps track of that and switches it back and forth as the mouse moves around and hovers over each window. So all I'm going to do is I'm going to change it to a wait cursor, the little spinny thing. It's going to count to 10,000, and it's going to write something to the debug console, which is the, you know, debug output, you know, that one, the one that gets all the messages while your program is running. That's what debug.write does. It's very helpful sometimes when you want to know what your program is doing, but you don't want to show anything to the user. Yeah, and it's really cool if you haven't used this much. You know, typically 99.9% of the time we as developers are writing our code in debug mode and testing it in debug mode, but you also want to make sure you change it to release mode and run it and test it a little bit before you release it, because code like debug.write changes behavior when you're in release mode. None of these debug messages will show up. They don't go anywhere. All this code gets compiled as a no-op when you're in release mode. And other things can change. Your code may not even compile in release mode if you didn't do it right. You know, you can do things so that your code doesn't compile in release mode even though it compiles in debug mode. Similarly, your code can behave differently depending on, you know, how you write it in debug mode versus release mode. So anyway, so in debug mode, these debug messages are very useful for diagnostic purposes. But yeah, so it's just going to write the string, 10,000 of these strings to the output console, and when it's done, it'll change the cursor back to the default cursor and pop up a message box. So let's run this and see what happens. So that's my first button here. I click it. Let's say debug, Windows, output. Yeah, here it is over here. It's putting all of my little messages out there. You know. Yeah, so apparently already finished. Okay, operation completed successfully. But it probably took about 10 seconds for it to count to 10,000 doing that. But, and I'll do it this time again while watching it, change to an hourglass, we count to 10, and eventually it writes all those numbers out there and completes. So it wasn't too bad, but of course I intentionally did it so that we wouldn't have to wait long. I could have made it count to 100,000 and we could come back at the end of class and check on it, but no, I did it on purpose. Okay, so you get that one. The next one that I wanted to show you is using a thread, a background thread. And the point of this one is to do the same task, but just do it in a separate thread while we free up the UI to be able to interact with it again. One of the things that this enables us to do is take advantage of cancel functionality. What if we kick off some long-running process and we think, oh, dang, I fed it the wrong data, I want to stop it. Well, with the first way, I don't have any way to stop it because I've lost control of the user interface. But if we do it in a background thread, then our user interface can continue to respond and I could put in a cancel button. So that's what I'm going to do. And, you know, I could have had a OK and a cancel button, you know, a start and a stop button in the UI, but instead I have one button. And when I start it, I change the text of the button to say cancel. And when you cancel it, it goes back to start, you know. So I just change the text back and forth to toggle it. Okay. And another thing that gives us is the ability to support a progress bar. So this is how you do progress bars. If you have a long-running process, you have that process every time through the loop or every 10 times through the loop or whatever, send an event back to your UI thread to say, hey, I'm 2% complete now, whatever you want to do with that, right? You don't say, get access to the progress bar and change its value to 2, because that would be tightly coupling. You say, hey, by the way, UI, I'm 2% done, and let it display that however it wants to, right? Okay, so let's look at that. So I got a whole bunch of new code that showed up here. I have this background worker. So this is a variable of type background worker. I just made it a property to make it convenient. Here's my button click event. And as you can see, if I don't have a background worker already, I create one and I do some stuff to configure it. What am I going to do to configure it? Okay, when I tell you to start background worker, here's the function that I want you to call. That's how you will start this background process, is by calling this function. Anytime that calls, wants to send an event to the UI to say that the progress has changed, I'm 2% done, I'm 3% done, I'm 4% done, here's the function that I want to get called whenever that event fires. Similarly, when it's done, call this event handler to signal that the process has completed. Okay, that's basically my configuration. You know, obviously, I have to set these flags. If I set these to false, then even if I define this, it's not going to work. You have to do both. You have to give it a method and you have to tell it to behave this way. Okay. All right. Then I say, if it's busy, that means I have previously clicked start. Then that means that they clicked on the button because they want to cancel it. Maybe it's easier to do the other side first. If it's, Is that right? If the background worker is not busy, yes, that's right. It's not doing anything right now. Then I'm about to call run worker. So I want to say, well, first, set the text to cancel, make the progress bar visible, and set the progress to 0. So I'm just initializing the state that I want it to be in when I'm running. And then I say, okay, now start the job. If it is busy, that means it's running and they clicked on the button. So if it's running and they clicked on the button, that means they want to cancel it because it's running. So now I say, set the text back to the original text, hide the progress bar, and then cancel the job. So that's how you do it. The rest of the stuff down here, here's the function that does the work. Here's the function that handles the event for progress change. Here's the function that handles when it's completed. So we'll look at those. Similar to the other example, I'm counting to 10,000 and I'm writing stuff to the debug console. But I've added some stuff in here. Inside this loop, I say, hey, check this cancellation pending flag. So this background worker object has a property in it that can be edited while my loop is running. Think about that for a minute. So the background worker object, I have access to that object. You know, I called this method and I'm in a loop, and yet the value of this variable could change from one iteration of the loop to the next. So that's some of that parallelism going on there that we were talking about. So if the value of that changes to true, then I want to say, take this do work event args, set this to true, and return. And whoever called me will look at that value and see that I set it to true, and they will say, oh, hey, by the way, we got a cancellation here. All right, so another thing that I added in here each time through the loop is just a minimal sleep. One is for 1 millisecond. I just want to sleep at all. I don't want to sleep for any length of time. I just want to say, just sleep. And what that does is it gives back control to Windows so that it can let other threads do their thing. Then I say, here's how far along I am. Each time through the loop, I update this, 1%, 2%, 3%. And the report progress is calling that event back to the UI. I would say, so this is calling report progress every time through the loop. Why should I call report progress 100 times saying I'm 1% complete? Shouldn't I do this only if it changes from 1 to 2 or from 2 to 3?
Because don't you want it to increment?
Yeah, but think about the math involved there. I is looping from 1 to 10,000. But the value of this expression is only going to change every 100 times it's called. So it's going to be a value of 1
Oh,
100 times.
then that's 1, and that would equal what, 1%? Oh.
Yeah. So if you wanted to optimize this, there's probably an opportunity there. You could probably do something like if I minus 1 times 100 over 10,000 is not equal to I times 100 over 10,000, right? So only do it if they're changed, if the value changed. But I didn't do that for this. I'm just pointing it out. You know, the code is easy to read, but it's not necessarily optimized. It's going to call report progress, which is right here. Well, yeah, so report progress is going to cause the event to fire, which is going to cause this function to be called. And all it's going to do is say, hey, change the value of this progress bar. So it's pretty cheap, you know. It's not going to cause a huge delay or anything, but it's not going to be zero effort to do that. So, you know, dial your own level of pain there. If you want to optimize this stuff, you know, feel free. I don't know, you might even hit F1 or, you know, go look at the API documentation on this report progress. It may already have that built in. It may say, you know, the last time you called me, you passed me a 1, and you're passing me a 1 again, so I'm just going to eat it. I don't know. Or the progress bar may say, you're setting me to a value that I already contain, so I'm not going to do anything. It may already be optimized like that, but it's stuff to think about. Anyway, okay, so then the whole loop executes. At the end, we report 100%. And that signals that we're done. Okay, so at the end, the run worker completed gets called, and I could have called run worker completed because I hit the cancel button, or it could have finished normally, so I show a message box either way. And so there you go. There you have an example of the code. So let's go watch it run. Oops. Where'd it go? Okay, here it is. All right, so we clicked the first method. It took 10 seconds to run. We click this one. Still taking a while, but we're getting those events to say that the progress is changing. It's churning right along. I can click cancel. It says operation cancel, pretty quick. But, you know, my user interface, while it's running, you know, my user interface is pretty responsive still. So all that's happening on a new thread in the background is doing its thing back there. Okay? Pretty cool. All right, method 3. So they have this thing called a thread pool, and think of that kind of back to the example of having the multiple people waiting for the lunch seats so that they can eat their lunch. So maybe we got 10 people at Chick-fil-A holding their sandwich, but there's only 3 chairs at the table that are available and they're all taken. Well, that's kind of like a thread pool. And so we've got some cool stuff that they provide us in .NET and C# to take advantage of thread pools without having to know how to create them and define them and configure them and manage their progress and stuff. So let's go look at what that looks like. Let's go. Here we go. So this function right here. So it's using a parallel.for. Now it is similar to a for loop, right? Except that I'm calling a function and I'm giving it the from I equals value to value, and I'm telling it what to do inside the loop as if I'm calling a function. I've demonstrated a number of things here that you may not have seen yet in C# that you can do, and that's okay. That's why it's a good example. But the thing to focus on here is just the parallel for. So for I equals 0, while I is less than 100, do this. That's all it's saying. But the cool thing about it is I've chopped it up. If it's possible to take your work, your 10,000 things that you need to do, and you can chop it up into buckets of similar work, then you can use a thread pool. And each thread in the pool will pick up a different unit of work and it'll execute it for you. So as an illustration, I went from counting to 10,000 to counting to 5,000 100 times. So I've gone 50 times as much work being done as the original two examples. 50 times as much work is being done. Or 50 times as many iterations, I'll put it that way. So that's one thing. And let me just run it and show you. So this is the third button. That took less than 3 seconds to do 50 times as many iterations. 3 seconds instead of 10 seconds. So 50 times as many iterations in less than a third of the amount of time because I'm using a thread pool. Why is that so fast? A few reasons. Number one, these computers are really good computers. They have a whole bunch of cores and several processors times that many cores. So your thread pool, instead of just having 10 threads, maybe you have many, many dozens of threads that you could use realistically, practically in your thread pool. So it behooves you to figure out ways that I can chop up this long-running task into small bite-sized pieces, because I got lots of cores sitting out there waiting to be asked to do something, okay? That's one thing. The amount of parallelism that I have available, that I have capacity for on my hardware is astounding in this day and age for cheap. It's a great time to be alive as a developer. Next, I have used language constructs here, which themselves are written to be very optimized and take advantage of parallelism. So this innumerable range, what that does is it says, give me 100 of something. So 100 integers, 1 through 100. And for each one of them, create a string and convert that string to an array. So the way this line is constructed is meant to be highly optimized and parallel in how it does it. And so all it does is says, hey, give me 100 empty strings, or strings that start with thread and a number. Very fast. I mean, this thing probably runs in a few milliseconds, okay? Same thing, change the cursor. Here's my parallel for. Like I said, this is splitting it up into 100 bite-sized pieces, and each one of them are doing 50 times the amount of work. Yeah, I guess it's actually 5,000 times as much work. Check my math there, but it's doing quite a bit more stuff. The next thing I'll point out is, if you think about it, well, obviously this is going to be a whole bunch faster than the first two examples, because the first two examples, I was calling debug.writeLine in a loop. And each one of those calls is very expensive. It's like saying, open a file, write a line of text to the file, and close the file on your hard drive. Just not that bad. It's opening up exclusive write access to a resource, all of that conversation and locking that has to go on with that resource, doing an operation on it, and then giving back that resource so that the next person can take advantage of it. It's very expensive. So my next tip is, look at what you're doing in every one of your loops and see if you can optimize it. So in this algorithm, I'm still doing the debug write line, but I'm doing at the end. And all I'm doing inside the loop is string concatenation. Taking an existing string object and adding a little bit of text to the end of it, appending to it, is orders of magnitude less expensive than doing a console write line or a debug write line or a file.write. So consider that, what you're doing inside your loops, Try to make it as cheap as possible. Next, I showed you another method. Array contains this method called for each. If you have a collection, doesn't have to be array, it could be a linked list or a queue or a stack or whatever kind of collection that you've got in .NET. If you have a defined collection that's been provided for you from .NET and you need to iterate over it, there are very fast, optimized, built-in ways of doing that. So here there's this array.forEach. I say for each of the strings in this array called parts, do a debug write line. Boom, milliseconds. Okay? And then I change the cursor back and do the message box. So there's several reasons here why this, taking advantage of all this parallelism and different techniques, is orders of magnitude faster than the first two techniques. And that's what I wanted to point out to you. Okay, so back to this. Method one, really slow and yucky, right? Taking advantage of nothing and making the user wait for us. If you just want to do the same thing without putting much thought into it, do the same thing but do it in a background thread and add a progress bar to be nice to your user, to give them some. So they've done these studies of Windows user interface guidelines where they have said that if a process takes the same amount of time but you give the person some eye candy to look at while it's running, they're less stressed out about it. They're less bothered by how long it takes. So just the fact that you add a progress bar to your program is going to make them happier with it. So that's method two. Method three, use a thread pool and boom, a lot of these problems are solved. Now they don't have to wait at all. That's the best. And method four, so you notice the way I did that, this is my button click event, right? So it's really, really fast, but imagine that the work took much, much longer. And then I'm still going to be sitting there with the spinning hourglass waiting for this process to finish. So if we wanted to extend this even further, we would take that code that itself is very parallelized and optimized, and we would move it into a background worker. And I'll leave that to you guys to play with. But you can see how I'm basically combining the techniques I used in this method with what I did for the previous one, with the progress bar and the background worker, right? Hopefully you can extrapolate from there. Any questions about that before I close it? Okay. Okay, so events. So sometimes we want to do our own events. So when all of the level of functionality we need is something like a progress bar, use progress bar. That's what it's there for. It works great for it. However, sometimes that our needs extend beyond what we can cover up with just a progress bar. And again, we still want to stick to that loose coupling concept where we don't put a bunch of UI related code into our background processes, our business logic. Say we want to, instead of updating progress bar, we want to simply append to a text box. You might think in terms of if I'm doing a game, at the conclusion of each player's turn, I send an event to say, this is what just happened. Add this string to the end of the game log, right? So I send an event with a string attached to it, and the UI code picks it up and says, oh, here's your string, listbox dot insert, and you insert it at the end of the current contents of the list box. You append it. So, in that case, you're going to have to kind of do the event yourself and call the text box code from the UI. So that's just a very simple example of why we might need our own events. Like I was saying, if you have a game loop and not all of your events result in something changing in the UI. Like for my implementation of the Wumpus game, I send a message to the UI and say, I need you to go get me a turn what you want the user to do. And then I sit there and I wait. I go to sleep and I wait until I get an event that comes back that says, here's player one's move. Well, the UI displays a text box or whatever, says, what do you want to do? They type in their text and they hit go, or you give them 3 buttons. Do you want to move? Do you want to shoot? Do you want to jump? Whatever. And they click on the button, and in your code you say, okay, here's the move. Let me send an event back over to the game and say, wake up, process the user's move. You know, you're sending events back and forth with each other. They're not necessarily tied one-to-one to user interface functionality. They're doing internal game stuff. Another good example is I send an event, after player one's turn has been processed, I send an event to say it's player two's turn. Well, on player two's turn, I call the large language model Docker container code to say, you are in a cave. You can hear wings flapping close by. You know, whatever other things. And I say to the large language model, as if you're talking to, let's say, ChatGPT, I say, your options are, you can tell me to go south, you can tell me to go north, or whatever. I tell the AI its options, and then I say, please answer as if you were a player in the game of Hunt the Wumpus. And if I put all that text together and make that my query to the large language model, the answer that I get back is, ooh, I'm scared. What shall I do? I'm afraid that I might just, whatever. It responds appropriately to my question. And at the end, it says, I want to go south. So I can parse that out and I can say, oh, the AI player wants to go south. Then I can process their move. But it has nothing to do with the user interface. But that event handler has to talk to the AI and get the response back and process the result that it got. So it's another example of not all events have to do strictly with the UI. We want our own events, and that's the motivation for doing this. Okay, so when we talk about our own custom events, we have these terms: an event, a delegate, and we have event args, the little object that gets passed to the event handler that has all the data that that event might need. We can derive a class from event args. The event args class has a string value. So if you don't have anything other than just a string that you need to pass to your event handler, just use event args. It supports that already. And if you don't have any data, you're just letting it know that something happened, you can pass eventargs.empty, which is just a cheap way of creating an event args object that doesn't have anything in it. Again, just a little trick. That's just like one of these, man, why am I creating hundreds of these event args objects in my code that then the garbage collector has to clean up? Well, there's one static one called empty that .NET provided to us that everybody shares because it doesn't have any data in it. So we can just pass that around, and it doesn't litter our memory with stuff. In the days when I was learning to program in .NET, and for a while after that, they had a rule that any event handler, in order to use these delegate and event patterns and stuff, your event handler's signature, the signature of those methods, needed to accept 2 parameters. The first was an object reference to whoever sent the message. And sometimes you could make your logic do different things based on what the data type was of the reference that you got. Using reflection that we've talked about, you can say if object.getType is, a background worker. Oh, okay, this is coming from the background thread, then do this. But they don't really enforce that anymore. If you go out there and you look for sample code on events and event handling, event passing, and all this kind of stuff, you're going to see people just have events that don't take any parameters or events that take custom parameters. They don't have sender, they don't have event args necessarily. To me, it's just a little lazy and sloppy, but that's kind of where they're going. You know, we're in C#, we're trying to compete with all these Java developers and Python developers, and where it's a wild, wild west and you can do whatever you want to. It's not strongly typed and all this. And a lot of these patterns are starting to creep in because they're trying to appeal towards getting Python developers to come use C# more for, you know, I don't like it. I don't feel like it's a good, I like the convention. Mainly because I like code that's readable. When you're looking through a bunch of methods in a class and you come across one, it's like, oh, object sender, comma, event args E. Oh, that's an event handler. You know, I recognize it. If you just start coming down with some, and you see a method that's void, do something, custom class X as a parameter, is it an event handler? Maybe. Is it used for an event handler and something else? It could be. I don't know. It's just kind of sloppy and loose, and I like the convention. So I would still recommend to you, if you're creating an event handler method, make the signature take an object and an event args, because it's just good practice. It's a good pattern. We didn't gain anything as Windows developers by losing the requirement to follow that convention. Maybe that's the best way to put it. Okay, next is subscribers. So if you've got this event sitting there, just because you've defined a function with a particular signature, and just because you've got a way, or you have some work that does, and you have some other code that needs to fire it, there's some plumbing that needs to go on in between there. So the event handler, great, we've got a method with the proper signature, and this keyword delegate is, I don't know, have you ever worked in a language like C++ or C before it? If you're going to define a function, you are required to provide a prototype for the function, and all it did was define the signature of the method or the function. You had to define what the return type was and what parameters were and what the name of the function was, you know, a signature of the, yeah. Well, if you're going to create an event handler, you need to use the delegate keyword, and you know, you'll just say like public delegate and the signature of your method. And that keyword of delegate lets the compiler know, oh, this is probably going to be an event handler. So you've just defined the signature. That's all it does. It's not the function. It's not triggering. It's not doing anything. It's just saying, hey, I need a delegate here. I need to define what this event is. Then we declare a variable of that type. It's like, well, what is the variable containing then? And what it happens internally is that declares an array. And that way later when your code is running and you say, whenever I trigger this event, I want you to call that method, you take a reference to that method and you add it to this array so that when the event is triggered, it looks in that array, and each method listed in that array, it calls it and passes the data to it. So it's all the plumbing that happens to support these events. So triggering, you know, when we trigger an event, is looking at that variable, and for each subscribed reference in that variable, in that array, we call the function or call the method. Yeah, and then a reminder from my comment earlier, this is when that starts to apply. We can't call UI events from a non-UI thread. So anytime you're triggering and you want that execution to happen on the UI thread, you have to use this invoke thing. So I'll show you an example here of what this looks like. So the first line here, public delegate void custom event object sender event args e. So void and the rest of that, that's the signature of my event handler. And all I've done is I've said, this is a delegate. It's something that can be called as an event handler. The next one, the public event, that's the array that holds the references to people who've subscribed to it. In order to subscribe to it, all I have to do is plus equals the name of a method. And now I've got a method that will be called. And you can do it multiple times. You can have multiple different methods that all get called. And if you have multiple, they get called in the order that they were added to this array. So the order of the subscriber. And then the last four, you'll commonly see this pattern in your code that's called to trigger the event. So the if statement down here is how you trigger the event. It's like, okay, my progress bar needs to move over. I need to trigger a progress changed event. You'll say, first of all, is invoke required? Am I running on a non-UI thread? And if so, then I call invoke, which, like I said, packages up a bundle of context and then places it in a queue that the UI thread comes along and picks up, executes on the UI thread, and then we get notified that that is done. So we only want to do it if invoke is required, because it's expensive, more expensive than not doing it. But if invoke's not required, just call it. You know, where is it? Oh, I think this, yeah. No, I think this is supposed to say custom event, not on custom event. Because custom event is the name of the delegate. So, my bad. I typed this, I didn't copy it from a compiler. Do you guys get that?
No.
Can I change it on the fly? Am I that? Why didn't you do that? Okay. Yeah, so this is supposed to say custom event, because that's the name of this variable, custom event. Remember, the event is the, yeah, I think that's right. Any questions about that? Sorry, I botched the example there at the end, but
No, it's okay.
so that's basically all the pieces that you need. Obviously, you wouldn't have them in this order. There's going to be other stuff in between all of this stuff, but that's all the pieces that you need in order to create a custom event, define what happens when you call the event, and trigger it. And another little note here, sometimes when you have a long running process, even if it's in the background, you want to give back control and give the user interface an opportunity to respond periodically. You can call application.doEvents, and that calls, it utilizes a piece of the Windows event loop that's underneath there to just say, you know, I want to pause and I want to go give .NET a chance to work on stuff that's in the queue. And it'll work on all the events that are in the queue, and then it'll come back to you and you can continue doing it. So you're still holding on to exclusive access of the user interface. You're just giving Windows a chance to let somebody else have a turn, and then you take it back when the queue's empty. Similarly, another way to simulate the fact that you're not hogging the resources, is you can just call thread.sleep and give it a number of milliseconds to pause. And when you do that, while your thread is asleep, other threads, such as the UI thread, can be processing events, and then you'll wake back up again and take control again. So that, keep those two things in your back pocket, and they might come in handy when you're trying to do multi-threaded things or trying to get a lot of long-running tasks work done in your UI.
Similar to like the interrupt one, where it was like taking 1 second away, okay.
Yeah.
Okay.
Yeah, you could do this inside your loop,
Mm-hmm.
or say every 100 iterations, call application.doEvents. And these are, I don't use these much anymore with the advent of multi-core processors and thread pools support being so accessible. Like, 20 years ago when I had to develop my own thread pool, if I wanted to use one, okay, give me a week while I go write that code and debug it and make sure it's working okay, and then I can come back to it. But now it's just, oh, wait, what was the syntax? And you do a quick Google, how do you do the parallel.for again in C#? And, oh, there's an example, copy and paste, and you're off to the races. So now it's very easy, very accessible, very convenient. So you don't use these much anymore. But like I said, just file them away in your back pocket, because once in a while you'll have a situation where they come in handy. And that's pretty much everything I wanted to cover here. Like I said, after I shut this down, I'll show you where I'm at with my project, and that will be fun. But we've talked about reentrant code concepts. We talked about the 4 different kinds of synchronization objects, different kind of threading and WinForms application behavior and stuff that we need to know, the idiosyncrasies of the UI thread, and a bunch of different patterns. The progress bar you'll probably use a lot. The background worker pattern with the progress bar is very helpful, very common, very approachable. Parallel.for is extremely powerful. It takes a little bit of work. Like I said, you need to chop your work up into smaller bite-sized pieces and then distribute them across the instance of the Parallel.for. Back when I was doing my PhD research, I was teaching in Missouri at the time. Had 4 classrooms like this that I, taught in. What I would do is I wrote a little piece of software that ran on the taskbar in each of the 30 stations in 4 different classrooms. And so it was just sitting there, running, listening. And then I would go back to the teacher station, and I wrote a program that would say, okay, I want to run this piece of work, process this chunk of data. And I would send a chunk of data and what I wanted to do to that data to all 120 machines. And it was like I had my own thread pool set up. So those 120 computers would receive the message, they would do their unit of work, they would send me a message back at the teacher station that says, hey, I'm done, here's the results. I would file that away in the database and send them another chunk of work. And I would sit there and basically just take a nap on the floor of the classroom for a few hours in the middle of the night. And then I got an incredible amount of research done at the time. But now I'm like, with one of these machines, I could do 10 times that much work with just one machine sitting in my office at home. So it's a great time to be alive as a developer, like I said, if you know how to take advantage of it. All right, any questions? Excellent.